Hi, everyone. My name is Yu, and I'm from Purdue University. So my mentor is Xiangyu Zhang, and I'm fortunate to present my work today. My work is titled Cost-Effective Attack Forensics by Recording and Correlating File System Changes. So let's first look at some recent trend on IoT device. You can see there is a very significant increase of IoT attacks worldwide from 2020 to 2012. So it increased 3 times in the past 4 years. And in 2012, the amount of the IoT attacks already over 100 million. So in this sense, the attack forensics are very crucial. There are 2 main parts in attack forensics scenarios. The first part is the provenance systems. A provenance system is designed to check the history of data from its creation to its current state. It records the metadata about data, including like where this data come from, who created this data or modified this data, and how this data are being transferred over time. And the second part is the integrity and the trust. We want to make sure that the data is not corrupted, and we also want to make sure that the data is come from a reliable source. And for the causality analysis, we will pass this provenance data to generate the final dependence graph, and then we will perform the forward and backward analysis from the symptom event. Okay, let's look at a real example. The audio log is widely used by existing attack forensic systems. Let's first look at this figure. It shows like there is a process read from a remote IP and then write to a file. As a result, when we pass this data, we will generate these provenance graphs. And when we do the dependency analysis, we will start from the symptom event. In this figure, it was called main.c, and then we will do the backward analysis and identify the real root cause, the remote IP address. So next, let's look at some existing provenance systems. The first category is the kernel-level syscall API monitoring. So this category, they mainly rely on the Linux audit subsystems, for example, the SPADE systems. They will monitor the syscall interface, and they will create log entries when some syscall match the auditing rules. And the next part is the kernel-level security API monitoring. So in this category, they instrument the OS kernel for auditing purpose, for example, the LPM system. And this will facilitate the whole system provenance collection. For example, a lot of this system, like Hi-Fi or Camoflow, they all come from this category. So recently, there are a lot of eBPF-based monitoring. They rely on the eBPM framework. There is a recent work called eAudit in last year's security and privacy. And the advantage is that they can intercept a subset of forensics-related syscall entry and exist on demand. Okay, so a lot of people have talked about the limitation of all these audio logs. For example, every process output may be assumed to be dependent on all preceding input. And this may lead to false dependence in the provenance graphs. So the last category is that people will leverage application-level information. For example, they will expose the application-level information to separate a long-running process into sub-execution unit. And then by integrating both the system-level information and application-level information, they can solve this dependency explosion problem. Okay, so now what is the limitation of all these existing provenance systems? We can think of like they are all record this log entry in a temporal domain. For example, when you have a write behavior, then it will generate corresponding write syscall. Right? Let's look at some real attacks on IoT hub. So how to define an IoT hub? For example, you can consider an IoT hub as an open hub running on a Raspberry Pi. And it was a central platform that enables multiple different IoT devices to communicate with each other, and also it can enable the IoT device to communicate with external users or other systems. So this IoT hub have a set of predefined rules in its configuration files. These configuration files specify how this IoT hub interact with other devices. So the configuration file is crucial in these scenarios. And another feature of the IoT hub is that it will frequently do a lot of routine tasks. And these tasks are usually benign. For example, it will frequently ping some crowd and frequently check some IoT device to make sure they are correct. So here comes the first limitation is that it will log a lot of these high-frequent events which do not cause harm to the system or even change the system state. So later, if there is an attacker, it may send some payload. And this was a real attack because of some missing privilege check. So finally, the configuration files will be affected. So the second limitation is that it cannot identify unauthorized file changes from normal file changes. So our first insight is that these attacks are often in a low frequency. So we may imagine like, could we take this forensics area in a different perspective? For example, we may take a very low frequent snapshot in a spatial dimension. For example, we only record the file system state. In this sense, we only need to record the snapshot data change in order to faithfully recover the full system state. Another insight is that by analyzing file system state changes, we could extract some forensics content which can help us to generate a graph. So by nature, if we extract this content, we can understand the configuration attack in previous slides. So the next challenge is like, how do we infer the causality from state information? Because the causality is very important when we do the analysis. Our approach was inspired by the information retrieval technique. It's like we want to reverse engineering causality by correlating state information across different snapshots. For example, the data of file copies we can recover by matching file content, and the process read-write files can be disclosed by extracting the file and the direct names embedded in the executable session. So by doing this, we reduce this challenge to a content matching and analysis problem. This is the workflow of our systems. It consists of 5 different steps. In the first steps, we will do the snapshot analysis. We regularly acquire snapshots from the ZFS systems. These systems leverage a copy-on-write strategy, which snapshot only record the file system data changes. So in this way, we can easily determine a list of changed files. And the next part is we will parse the file. We propose a universal file model to represent the file in different formats. And this model was customized for forensics purpose. Let's look at some detail about this model. It's like it will contain a lot of forensics-related information, including metadata, like the data source, permission, location, and it will also try to contain API embedded in some executable script. So after we pass all these files into this forensics-aware format, the next part is that we want to generate the provenance graphs. So in this case, the input are this universal file model from both the symptom files and the change files between different file system snapshots. And we have predefined a set of data log rules. And the data log engine take all this input and will generate the final content provenance graph. Here I have an illustrative graph to highlight this process. We have the universal file model from a symptom event. And similar to information retrieval, we will match this symptom file with other files which are changed during 2 snapshots. We have predefined a set of data log rules, which it defines several different age types: the data flow age, the control flow age, and the content match ages. So finally, we will generate this content provenance graph, just similar like when you try to search something. You can imagine these symptom files as a keyword or document you want to search. And you can imagine the data log engine as a search engine. And then given these symptom files, you want to search all forensics-related content in other files. And finally, we will generate these graphs. So the next part is like, since this graph is very large, right, we want to highlight those ages related to the attack symptom file. So first thing is like, similar to PageRank, we want to rank those files which are most highly likely to the symptom file. We first do the age weight calculation. We assign a weight to each age in the content provenance graphs based on the file content similarity and their semantic coupling. And the next part is we do the node weight computation. Starting from the symptom files, we will propagate the age scores and calculate an important score for each node. And finally, only those nodes with very high scores are considered related to a real attacks. So we evaluate our systems on 5 different devices, including 3 mainstream smart home platforms, 1 Android phone, and 1 personal computer. How we select the attacks is we search all the attacks in recent years with detailed attack steps and reproducible POCs. And we manually label nodes and ages generated in these provenance graphs. And these are 16 attacks we run on 5 devices. For the personal computer, we reuse the attack script from the DARPA transparent computing programs. For the rest IoT device, we will use the provided reproducible POC. So we compare with 3 different baselines: 1 kernel-level provenance systems clone, and 1 application-level provenance system called Alchemist, and a recent eBPF-based provenance system, eAudit. The provenance data for the 3 baselines, they capture the interaction between the system subject and object. In this case, was the system log and application logs. For our systems, the provenance data is the forensics-related changes between different snapshots. We measure the runtime overhead by using a workload called Postmark. This was a file system benchmark that simulated the mail server behaviors. And the metric is we measure the ratio of the CPU time used by the provenance collection systems to that of the benchmark. And here is the result. Our system achieved the best performance in terms of runtime overhead. The average runtime overhead is only 3%, whereas the eAudit was 5%, and the rest are over 14%. We also measure the space overhead over 1 week. The metric is we measure the additional files created during this 1 week period. So for our systems, this overhead was those file change record we need for generating the provenance graphs. And for the eAudit and the clone was only the syscall logs. And for the Alchemist was the syscall logs and the application logs. So in total, our system consumes only 100 megabytes on average for 1 week, which other systems generate 6 to 12 to 20 times much more overhead than our tools. So finally, we want to evaluate the effectiveness of our attacks in attack forensics scenarios. The metric is that we use both our systems and the 3 baselines to generate the provenance graphs. Since we already manually labeled all these graphs, we will compare them to obtain a precision and recall. The precision is defined as the proportion of nodes in the graph being related to the attacks. And the recall is defined as the proportion of the attack nodes including in the graphs. So this was the result. And our system performed the best in terms of precision and recall. So the final conclusion is like we propose a cost-effective method which records the system state information, and we can infer causality out of this information. We develop an algorithm to compute weights for content provenance edges and nodes so that a weighted subgraph related to the attack can be determined. So finally, we develop a prototype and evaluate on 5 devices and compare with 3 state-of-art techniques. In the study of 16 attacks, our system performs the best. And that's all for my today's presentation, and thank you all for listening. I know like it's the end of the day, so I hope that you will enjoy this talk. Thank you.